Hey everyone, in this video we're going to talk about hyperbolic trig functions and their derivatives. You may have seen hyperbolic trig functions before, you may have never seen hyperbolic trig functions before, so either way we're going to explore them in this video, and I'm going to talk about how they are one of the most underrated trig functions out there. They're extremely useful, but I think because of their complexity, oftentimes people tend to forget about them or think that they're not that useful. But if you know them and get to learn them, they are actually quite fascinating and very helpful, especially in Calc 2. All right, so let's go. What are hyperbolic trig functions? Let's start off with our standard trig function. So what I have here is the graph of y equals sine x. So where does this come from? When you have one period of sine x, this is between 0 and 2 pi. So that is one period of the function sine, which really comes from the unit circle. So when we graph the point xy here, right, this is x and this is y. So when you complete this triangle, if I put an angle theta here, then notice that when we do our trig functions, opposite over hypotenuse is our sine. So in the unit circle, sine of theta is the opposite over the hypotenuse, which is 1. So we get y equals sine theta. And we can do the same thing for cosine, right? And so this, then it's really cosine theta, sine theta. And so what we're graphing here is the y equals sine x. So it's just we're taking the y values from here and all around the circle, right? So when theta is 0, when x is 0, is 0. Then when you get to pi over 2 over here, this point is 0, 1. So sine is 1. So sine of pi over 2 is 1. And so over here at pi over 2, it's 1, and so on. So these points, as you go along the unit circle, here the point is -1, 0. So sine is 0. So over here at pi, you end up with 0 again, and so on. At 3 pi over 2, you're -1. So the sine value here, the y coordinate, is -1. So what we're doing then is going around the circle, taking the y coordinate and then translating it to the xy plane. And so that's how we get the sine curve, one period of it. This is 2 pi. And then as you continue on and on, you get the entire curve. And so the hyperbolic trig function, so I'm going to look at y equals hyperbolic sine. So y equals, and we call it sinh of x. So what is hyperbolic sine? The hyperbolic sine function, instead of us looking at the unit circle, the reason that this is called a hyperbolic function is because the h comes from the unit hyperbola. What do you mean by the unit hyperbola? The unit hyperbola is x squared minus y squared equals 1. And so what does this hyperbola look like? So here's our unit hyperbola. And so meaning it comes from x squared minus y squared equals to 1. So the unit circle is x squared plus y squared equals 1. The unit hyperbola x squared minus y squared equals 1. So if we do the same thing where I have my unit hyperbola here, and we place our theta as we did before, right? Then this is x and this is y. And so this point is the point xy, which ends up being just like it was for the unit circle where it was cosine theta and sine theta. The interesting thing about the unit hyperbola is that these end up being so hyperbolic cosine. So hyperbolic cosine of theta and hyperbolic sine of theta. So cos and sinh. And so when I look at the function, just y equals sinh theta, just as we did here with y equals sine x, what we're doing is graphing the y coordinate as we move along the circle. When one period is 0 to pi, we graph the y coordinate, and that gives us the sine curve. So if we do the same thing here, right, if I graph just the y coordinate, y equals sinh theta, then as we go along the hyperbola, we are going to get the graph of sinh. I just want to show you real quick what that looks like to move this point along the hyperbola. So let's go to Desmos for that. So here we have the point moving up about the hyperbola. So notice the triangle as the point moves away from 0, 0, then the triangle changes. And so this, as we move along the hyperbola, the y value is what is going to create the curve sinh. So then when we take just the y value of this triangle as we go along the hyperbola, y equals sinh theta, then and graph it in the xy plane, so on xy plane I guess, then it becomes y equals sinh of x. And this is what the graph will look like. So this is y equals sinh x. And now this is the definition of the hyperbolic. It's quite interesting. So sinh of x is defined to be the average of e to the x plus e to the minus x. Oh, sorry, wait. Sinh is minus e to the minus x over 2. And so that's what sinh x is equal to. And so essentially, if you think about e to the x, that's the function that goes and has a y-intercept of 1. So this is y equals e to the x. And then e to the negative x, or in this case, negative e to the negative x, right? Because I'm going to be subtracting. So think of this as e to the x plus a negative e to the minus x. So what that one looks like is the flipped of this. So you're going to have n of negative with a negative exponent there. So you end up with something that looks like that. So this is y equals negative e to the negative x. So when you add these two up, right, so you get sinh of x, which is this function. Very interesting connections here, right? It's also so the sinh x is the y value as you have a triangle that moves along the hyperbola, and then it is also the average of taking e to the x values and the negative e to the negative x values and averaging them up. So notice that here, right, that's 1 and this is negative 1, and so when you add those you get 0 and so on. So if you pick the one over there and one over here, add them up, divide by 2, you're going to get that value, and so on. So this is a definition of sinh, which then brings us to, okay, so if that's sinh, what are the other, because these are trig functions still, they're hyperbolic trig functions, so instead of following the unit circle, they follow the unit hyperbola. We're still going to have all the other ones, the other 6 trigonometric functions, but in this case 6 hyperbolic trigonometric functions. So we're going to have cosh x, and cosh is equal to e to the x plus e to the negative x divided by 2. So I started to give you the one for cosh. And then hyperbolic tangent, and you can call them hyperbolic sine, hyperbolic cosine, and then because all the other ones you can't say, well, yeah, like tang doesn't really work. So we usually say hyperbolic tangent, and so you can just say hyperbolic sine, hyperbolic cosine for those instead of calling them sinh and cosh. So hyperbolic tangent is still just like tangent, is sine over cosine. So then this is going to be e to the x minus e to the minus x, and then when you divide it by this, the 2's will cancel, so you have e to the x plus e to the minus x. So that's hyperbolic tangent. And then you have all the reciprocals. Hyperbolic cosecant of x is 1 over sinh x, right? The reciprocal of hyperbolic sine. So you could also write it as 2 over e to the x minus e to the minus x. But I'm just going to say these are still reciprocal functions. So hyperbolic secant is 1 over cosh, and hyperbolic cotangent, we already wrote tangent, hyperbolic cotangent is 1 over tangent, 1 over hyperbolic tangent of x. So these are your 6 trigonometric, hyperbolic trigonometric functions. So now if I want to find a derivative of, say, sinh x, how do I find that? So in order to find a derivative here, I'm not going to resort to the definition. We're not going to do f of x plus h minus f of x. Now we have other tools. We have implicit differentiation, but we also know that the hyperbolic sine is equal to e to the x minus e to the minus x over 2. So I can just take the derivative of that instead. So I'm going to say the derivative of sinh is really the derivative of e to the x minus e to the minus x over 2, and take the derivative of that. So this is, what is this going to be? We can pull the 1/2 off to the side, and it's just really times e to the x minus e to the minus x. So the derivative of this, then, it will be 1/2, right? My constant stays there. The derivative of e to the x is just e to the x minus the derivative e to the negative x. The derivative e to the stuff is e to the stuff times, by chain rule, the derivative of the stuff, which in this case is a -1. So multiplying that -1 in, I'm going to have e to the x minus times that -1 becomes plus e to the minus x over 2. Which, do we recognize that? That is hyperbolic cosine. So that means that the derivative of sinh x is cosh x, right? And remember, with standard trig, I know that the derivative of sine is cosine. So that still remains. Now what about the derivative of cosh? Let's do the same thing. I know that cosh, hyperbolic cosine, is e to the x plus e to the minus x divided by 2. So you can kind of see already, we're going to keep the 1/2, and then the derivative of e to the x is e to the x. The derivative of e to the minus x is going to be e to the minus x times the derivative of negative x, which is a -1. So that's going to become minus, which is just really e to the x minus e to the negative x over 2, which we know as hyperbolic sinh x. So we can say the derivative then of cosh is positive sinh x. So there are no negatives here. With standard, right, recall that the derivative of cosine was negative sine. But here we don't have the negative, it's just sinh. And that's because we are really taking the derivative of these quantities, and there's no negative that we can pull out. What about hyperbolic tangent? So let's try find the derivative of hyperbolic, oops, that's an x, of hyperbolic tangent. Any guesses what it's going to be? Is anyone guessing that it was going to be hyperbolic secant? So let's see. So there are a couple ways that we can do this. We can use the definition. I know that hyperbolic tangent of x is sinh over cosh. So we can do this. Or you can put the other definition, the e to the x minus e to the minus x divided by e to the x plus e to the minus x, but we might as well just use this one. So this is what we know about hyperbolic tangent. So then the derivative of sinh x over cosh x, then we're going to use the quotient rule. So it's going to be the bottom, so low, so cosh x times the derivative of the top. So the derivative of sinh is cosh minus the top, which is sinh x, times the derivative of the bottom. The derivative of cosh is positive sinh x all over cosh square. And so I really have cosh square x minus sinh square x all over cosh x square. So now what do we do with this? Now the interesting thing, because these are still trig functions, a lot of the identities are very similar or the same. So what do we know about the standard trig? The identities. So in standard trig, the identity is that cosine square x plus sine square x equals 1, right? And so, but this is because we follow the unit circle. What about when we follow the unit hyperbola? So let me emphasize again that the reason that this is cosine square plus sine square equals 1 is because we follow, right, this along the unit circle, x squared plus y squared equals 1. So for hyperbolic, then, so for hyperbolic trig, what we're following is, I guess maybe I should have called those thetas, not to make the same x variable, not to confuse that. So when we have hyperbolic trig, we're following the unit hyperbola. So what is the identity? The identity then is going to be cosh square x theta minus sinh square equal to 1, which notice that's what we have here. Cosh square minus sinh square. So that means this is going to be 1 over cosh x square. But 1 over cosh is secant. So we get hyperbolic secant square of x. So they're starting to look very similar. So if I'm going to list the hyperbolic derivatives, we are going to have, I'm going to do my same little chart as usual. So I'm going to have f and f prime. So when we have hyperbolic sine, the derivative is hyperbolic cosine. When I have hyperbolic cosine, we have hyperbolic sine as our derivative. Hyperbolic tangent, our derivative is hyperbolic secant square. So they're looking pretty much like the standard trig derivative, so they're not that hard to remember. And then the only ones are now for our reciprocal functions. So hyperbolic cosecant of x now is going to be negative cosecant hyperbolic cotangent. So it's very similar. In hyperbolic secant is negative hyperbolic secant hyperbolic tangent. And so based on this, what would you say about hyperbolic cotangent x? What would you say its derivative is? Yeah, it's going to be negative hyperbolic cosecant square x. So essentially the difference between these and the standard trig functions is that all the reciprocals are negative. With the standard trig functions, all the cos are negative. So the cosine, the cosecant, and the cotangent are negative, leaving all the other ones positive, whereas here our main three are positive and then our reciprocals are negative for the derivatives. But if you remember the derivative of, say, tangent x, the secant squared, then the derivative of hyperbolic tangent is hyperbolic secant square x. So these derivatives hopefully are not going to be too hard to remember. And so how do you then evaluate derivatives and evaluate the functions? Let's try an example. Say, for example, we have this. Find the slope of the line tangent to f of x equals sinh x at x equals ln of 3. So I want to find the slope of the line tangent to, so that means I need to find the derivative. So m is f prime evaluated at natural log of 3. I don't know why I wrote it that long. I could have just said f prime of ln of 3. So let's find the derivative. So since f of x equals sinh x, then f prime of x is cosh x, hyperbolic cosine. And so now we evaluate it at natural log of 3. So f prime of natural log of 3 is our slope, which is going to be hyperbolic cosine of natural log of 3. But now how do I do that? Our calculators don't have hyperbolic cosines, so I can't just put it into a calculator, but luckily we do know the definition. We know, what do we know about cosh x? We know that cosh x is equal to e to the x plus e to the minus x divided by 2. And so now we can use that to evaluate. So that means that this is going to be cosh of natural log of 3. So x gets replaced with the natural log of 3. So everywhere I see an x, we're going to put in natural log of 3. So I'm going to have e to the natural log of 3. I chose that point, that value on purpose, plus e to the negative natural log of 3 divided by 2. So e to the ln of 3, what's that? E and natural log are the same base, so I just get 3. Now this, I can't just cancel the e and the ln, right? Because I have a coefficient there. This is really a minus 1. So let's rewrite that as, so this will be plus e to the ln of 3 to the minus 1, right? Properties of logarithms. So this negative 1, I can bring it as an exponent. So an exponent on 3 over 2. So now I can simplify it. So this is 3 plus 3 to the minus 1, which is 1/3 over 2. And you can get a common denominator here. Common denominator is 3, so what's this? 9/3 plus 1. So I'm going to have 10/3 divided by 2. Dividing by 2 over 1 is the same thing as multiplying by 1 over 2. So our final answer for the slope, being f prime of ln of 3, will be 5 over 3. Cool. So that's how we evaluate our hyperbolic trig functions. So just to practice, evaluate the following. Let's try A. Find sinh of 2. Let's try B. What about cosh of 1? And what about hyperbolic tangent of 0? I guess if we want to get a little bit more creative, I can add another one. What about sinh of the natural log of 5 minus 2? I don't know, just to make it interesting. So what about sinh of 2? That means that x is 2. So plug it into the definition of sinh. Sinh is e to the x minus e to the minus x over 2. So when x is 2, I'm going to have e squared minus e to the minus 2 over 2. So notice that this one is not as nice to evaluate because we don't have a natural log. So put that on a calculator and you can round to perhaps 3 decimal places to give an answer. Same thing here. Now here x is 1, so but it's cosh. So I'm going to have e to the 1, so just e minus, or plus because it's cosh, plus e to the minus 1 over 2. And so this one you could simplify a little, right? Is e plus 1 over e over 2. and get a common denominator, just like we did with the 3 above. Tangent of 0. Tangent is sinh over cosh, or you can think of it as is the e to the x minus e to the minus x over e to the x plus e to the minus x. So when you have at 0, you're going to have e to the 0 minus e to the minus 0 over e to the 0 plus e to the 0. So you'll have 0 over 2, which is 0. And now this one, here x is ln of 5, so you're going to have e to the ln of 5, so that's going to just give you 5, and it's sinh, so minus e to the negative ln of 5 over 2, and then you have minus 2. So in case you get this as the answer for a derivative, then this is how you would evaluate it. So this will be 5 minus that negative becomes the exponent of 5. So 5 to the negative 1, which is really 1/5 over 2, and then minus 2. So this one, what's this? Get a common denominator, right? So it'll be 25 minus 1, so 24 over 5 divided by 2, and then minus 2. This is starting to become just a very not so pretty fraction problem. Well, the 24 and the 2 reduced to 12, so I'm going to have 12/5 minus 2. Get a common denominator here, so that will be 5, so 10. So 12 minus 10 is 2. So you'll have 2/5 will be your final answer here. But my point is that when you have hyperbolic trig functions and you're evaluating them at a numerical value, that's when we want to come back to the definitions. Where did I write them? Yeah, right here. Sinh is e to the x minus e to the minus x over 2, cosh e to the x plus e to the minus x over 2, and then hyperbolic tangent is this one. And then the reciprocal functions are just 1 over the other ones that we found. Okay, in the next video, I'm going to talk about the inverse hyperbolic trig functions. And we'll do some more examples of derivatives with all of them. And because then how does the chain rule apply, right? If I wanted you to find the derivative of sinh of x squared plus 1, now the chain rule applies. And then product rule and quotient rule with these hyperbolic functions.